yesterday we got partway through describing the first scenario in which we end up with glide reflection as a generator. Okay, so I'm just going to start by reminding you what we did last. Okay, so here is the point where we had reached. Okay, we had supposed that some Friese group contains a half turn and a reflection in line 2. And reflection in line Q. Okay. So we eliminated the cases where Q is the center of F, or that Q is perpendicular to C, the center, at either one of the AIs or the MIs. And remember, AI is the image of this point that we chose A on our center C under tau I times. Same thing for the midpoint. MI is the midpoint of AI and AI plus 1. Okay, so we got to the point where we're assuming that Q is off of AI and MI for all I. And we deduced, we showed yesterday, that Q must be the perpendicular bisector of the line segment AMI for some I. Okay. Furthermore, we know that F contains half turns by assumption. Implies that F must also contain reflection in the perpendicular bisector of each line segment A and I, as I varies, right? We necessarily have, because we can compose our reflection in Q with these half turns to get to the perpendicular bisector of each of these line segments A and I. Okay. Right. That is to say, more precisely, I'm using the same method of conjugation to realize something about the symmetries that F must contain. So specifically, I have sigma sub AI composed with sigma Q composed with sigma sub AI inverse is equal to sigma sub sigma AI of Q. Right? And the image of this line Q under the half turn sigma AI is the perpendicular bisector of some line segment AMI for some I. Okay. Okay. In particular, what we have is that sigma P is an element of F, where P is the perpendicular bisector of our first line segment AM, that is A sub 0, M sub 0, right? Okay, basically I just want to give that a name, and we call it P, okay? So, now, if line A is perpendicular to our center C at point A, then not both sigma P and sigma A are in F. Okay, that is to say, if I take some other perpendicular to C, then why must it be the case that I can't have F contain both sigma P and sigma A? What goes wrong if F contains both of those reflections? Any thoughts on that? Well, what happens? First of all, how are the lines A and P related? Well, one thing that they have in common is that they're both perpendicular to C. If two lines have a common perpendicular, what does that say about them? Well, that means that, yeah, that they're parallel. Good. Thank you, Jordan. Okay, so what happens when we take the product of two reflections where the lines in which they are reflections are parallel? What kind of isometry do we get? Yeah, it's a translation. Good. Okay, but there's even more we can say. So let's say since, let's record everything we just said. P is parallel to A. which implies that sigma P, sigma A is a translation. A translation which furthermore has the following property. Sigma P, sigma A of our chosen point A is equal to sigma P of A, right? Because A is on the line little a, so it has to be fixed by sigma sub A. Where does sigma sub P take A? Well, remember we just defined P to be the perpendicular bisector of the line segment AM. So sigma P, reflection in sigma P takes A to M because we chose P to be the perpendicular bisector of the segment AM. Okay? So in other words, we've written this translation cannot be an element of the group F because it takes A to M, right? Well, all the translations of F are generated by tau. And tau of A is equal to A1, right? And M is the midpoint of A1, right? So we're always moving by a multiple of the distance from A to A1 for any translation that occurs in F, okay? But if this translation were in F, we would be moving by a non-integer multiple of the distance from A to A1. Okay, so therefore, that's why I say F cannot contain both sigma P and sigma A. Okay, so furthermore, we know that sigma P, sigma A is equal to sigma P times reflection in the center, sigma C, times the half turn centered at A. Okay. So what does this tell us? Well, this implies then sigma, or I guess I should say it this way instead, then F cannot contain both sigma P and sigma C, right? We know it contains sigma sub capital A because it has half turns. All right. So it might not seem like it, but this concludes our investigation of how we can add reflections to F2. Okay, so let's see what. This concludes our investigation of how we can add reflections to F2. Let's simply set F22 equal to the group generated by tau, some translation, the half turn at A, and reflection in the line little p, where little p is the perpendicular bisector of AM. Okay. So now I haven't said anything yet explicitly about light reflection. Right? But remember that we characterized light reflections as a product of either a reflection and a half turn or a half turn followed by a reflection. Right? This was back when we developed all the properties of glide reflections. We proved that we could take an arbitrary glide reflection and factor it in either of those ways. Okay, so that is how we'll get a glide reflection, by combining these. Okay. Okay. Right. So by our previous characterization, of glide reflections, F22 contains the glide reflection sigma p sigma a, which has axis C, right, the fixed line of the glide reflection, and takes A to M. Okay. So just notationally, let's set gamma equal to this product, sigma B, sigma A. Okay. Now, remember more facts about, oh, I'm sorry. Yes, so Keenan asked if we're getting the practice exam solutions. I'll send them out after class. Okay. Yep. Okay. So recall more facts about blind reflections. Since gamma takes A to M, what does that tell us? Well, it tells us that gamma squared is equal to tau, right? Because since A and M lie on the axis of our glide reflection gamma, and the distance from A to M is half the distance from A to A1, we know that when we apply gamma twice, we're just shifting by whatever tau did. Because remember, tau takes A to A1. Okay? So, what does this tell us? Well, this implies that sigma sub p is equal to gamma sigma A. Okay, why is this important? Well, now we can reduce our set of generators, right? So there's been a few occasions where we've looked at a group, found a set of generators, and found another set of generators, right? And most of those times, even if the sets of generators are different, the number of generators has usually stayed the same in most examples that we've seen. However, now we see kind of a different behavior, right? That is to say, F22 can be written as just generated by gamma, comma, sigma A, right? And the reason we're able to do that is because of this relation. This fact about glide reflections. Okay. Now, remember, we've seen a Fries group that contains glide reflections already, right? Namely, I think it was F2, right? Yeah. Yeah. Or, I'm sorry. Certainly, F21 has glide reflections, right? Yet we're not able to write F21 as having generators, glide reflections, as having any of the generators be glide reflections. Okay, so once we complete our classification, I'm going to show you a chart about how all these 7 types of groups relate to one another in terms of one being a subgroup of the other. And I think that will clear up why that is. Okay, but for now, just kind of interesting subtlety, right? Finding generators and relations in general is very hard. Okay, but it turns out that's why this result is so important, because we're actually able to make a complete classification of the symmetry group of a certain abstract characterization of patterns. All right. So, okay. Now that we have this compact form of how F22 is generated, we'll do the same thing that we've done for the previous 5 for each groups. We'll say a pattern having F22 as its symmetry group is the following. Our usual convention here, the solid dots are A's and the hollow dots are M's. Okay. So boom. Okay. So, okay. So again, I'll just say this pattern, which has a point of symmetry, symmetry, and a line of symmetry, and whose center C is not a line of symmetry. Of course, take the center line of this pattern, reflect about it, and I get a different pattern. Right? It's not fixed the pattern I've drawn here. Okay. So, what is the line of symmetry? It's the perpendicular bisector of A and M, right? If I reflect about this line P, I get the same pattern, right? Imagining that this pattern continued infinitely in both directions. You see that by flipping about this line, and in fact, any of these translated versions of that, the perpendicular bisector of any AI and MI will keep this pattern fixed. Okay. Okay. So this covers all the cases where a Friese pattern does not necessarily contain a glide reflection. Okay. We've seen a couple examples of Friese groups that happen to contain a glide reflection, and in fact, in this case of F22, we were actually able to reduce it to have a generator that is a glide reflection, but we did not assume that it had a glide reflection at the outset. We proved that given our assumptions that F contained half turns and a reflection in line Q, which was not decentered nor perpendicular to the center at one of the AI. Okay, so the final case is what happens if we assume that a Friese group has a glide reflection as a generator. And I feel like maybe there's some concern that we've said a lot of very specific things I just want to point out that don't worry, after we investigate this final case, I'm going to go back and summarize everything that we've done over the past 2.5 days having to do with the classification of Friese groups. Okay, we'll say everything all together in one go after we finish doing the work of the classification. We'll summarize our results. Okay. So finally, case 7. Suppose F contains a light reflection. Okay. Which we'll just call alpha. All right. And alpha must have axis C. And alpha squared is a translation fixing C. Okay. From this point, there are 2 cases. First case is that alpha squared is equal to tau to the 2n sum n. And the second case is that alpha squared is equal to tau to 2n plus 1, or some integer n. Right? Either alpha is an odd power of tau or an even power of tau. Right? Because remember, the characteristic of being a Friese group means that the subgroup of all translations is cyclic, meaning that once we have a translation that is in F, it must be some power of tau. Okay? And we'll address these 2 cases, even and odd, separately. So, case I. Why did I choose a lowercase Roman numeral? Just because we're already numbered 1 through 7 here for our cases for Friese groups. Okay, so starting with alpha squared equal to some even power of tau. Well, just by multiplication, what do we get here? We get alpha squared tau to the negative 2n is equal to iota. And just slightly rewriting this, we see that what this means is that alpha tau to the negative n squared is equal to iota. Now, so what do we have here? Altogether, what this implies is that alpha tau to the negative n is odd involuntary and fixes C. Right? How do I know alpha tau to the negative n is odd? Well, tau is even, right? A translation is even. And any power of an even isometry is also even. Alpha, I'm assuming, is a glide reflection, which we proved necessarily is, or actually we defined, is a product of three reflections, i.e. it's odd. So even plus odd is odd. This little piece of exponent arithmetic shows that I'm an involution. Right? So what is an odd involuntary isometry that fixes C? There's only one unique isometry that does that. Okay? Reflection in C. Yeah, thank you, Spencer. This implies that alpha tau to the negative n is equal to sigma sub C. Reflection in the center of our Fries group. Okay, which of course means, so in this case, alpha is equal to sigma sub C tau to the n, just by multiplying on the right by tau to the n, both sides of that equation. Okay. So now it turns out we can break it down into cases that we've already seen. All right. So let's say if our Fries group F does not contain half terms, we're necessarily in F11. Okay. And if it does, then what? Then we're in F12. Sorry, let me check one thing. Yeah, sorry, my mistake. I mixed up the indices here. This is F21. And we'll get to exactly why that is in a couple minutes. But okay, so case one, if my glide reflection is an even power of the generator of my translation subgroup, then my Fries group is one of the six we've already described. Okay? So again, this is back to the point I was trying to make when we completed case number 6. Even though F11 and F21 contain glide reflections, we're not able to write them as having generators, any of which are glide reflections. Okay. So again, once we finish case double I here, we'll go back and say a little more about that. But just run that as a background process in the meantime. Okay. Okay. So well, basically we'll start the same way. I'll just do a little algebra. Right? 2n plus 1. This implies in an entirely similar fashion that alpha tau to the negative n squared is equal to tau, right? I had one extra copy of tau multiplied over here, and I'm just leaving that on the right side of my original equation. Okay. Okay. So let's just set the quote unquote square root of tau to be gamma. That is to say, I'm just going to call this gamma. That gamma is equal to alpha tau to the negative n. Okay, which again is an odd isometry. Fixing C. Square is tau, which obviously is a translation. Okay, what does this tell us about gamma? And I suggestively named it gamma because that's the variable that we usually use for a glide reflection, right? So, in other words, so gamma is the unique glide reflection satisfying all these conditions. That is to say, with axis C and taking A to M. Now, how do I know that gamma takes A to M? Well, because A is on line C and alpha tau to the negative n fixes C, not pointwise, but fixes the line C, I know that it'll be somewhere on C. Okay, and furthermore, if I square alpha tau to the negative n, then I get tau, which takes A to A1. Okay, so if I'm doing the same shift in the line C, then in order to do it twice, to take A to A1, I have to take A to the midpoint of A and A1. Okay. Okay, so now just note that gamma to the 2m is equal to tau to the m. And gamma to the 2m plus 1 is, of course, tau to the m times gamma. So what does this tell us? This tells us that F, our Fries group, contains exactly light reflections of the form gamma to the, tau to the m gamma for integer m, of course, m. So therefore, we just let F13 be the group, which is just generated by gamma. Okay. So following is a pattern having F13 as symmetry group. Okay, same convention we've been doing all week. And what's the pattern? Okay. And we'll just say a little bit more about this pattern, which has no point of symmetry. Of course, no line of symmetry. But is fixed by a Lie reflection. Now, I claim that we're done. Well, that's not technically true. Right? How do we know that anything else we try to throw in to an arbitrary Fries group F will get us back to one of the 7 cases we've discussed so far. Okay, so let's take that final step. Now, I guess I'm kind of spoiling the fun here, but in fact, we're done. I mean, I kind of ruined that at the beginning of the week, right? I told you that there were only 7 freeze groups. So let us take the last step to verify that. Okay. So finally, suppose F contains isometries in addition to those generated by gamma. So, of course, just to be notationally clear, of course, still gamma has axis C, sorry, with axis C, and gamma squared equal to tau, the translational generator. So notice the following computation. If I take reflection in C after gamma and square it, what do I get? Well, I can distribute my exponent. Sigma C is an involution. So, oh, I'm sorry. Thomas asked if we had a test tomorrow. Right, I pushed it back to Tuesday just so we can actually cover the same content that is usually covered by test 4, right? Which is everything up through what we'll finish that today. Okay. Okay. Yeah, sorry I didn't look back soon enough. Okay. In any case, sigma sub C is an involution, and we just said that gamma squared is equal to tau. So what do we get? We get tau, right? Okay. So furthermore, this is with the fact that sigma C gamma is a translation. Right? Why is that? How do we know that sigma sub C gamma is a translation? Anybody have any thoughts on that? Well, remember, we said at the outset that gamma has axis C. Yeah, that's another good way to see it. Keenan says gamma is alpha times inverse of translation, which is still a translation. Yeah, that's a good way to see it. Another way to see it is that gamma, since it has axis C, has sigma sub C as its leftmost factor, right? So remember, so I'll just write this down really quick. Is a translation, since gamma is equal to sigma C, sigma R, sigma S, where lines R and S have common perpendicular C. So that implies that sigma C gamma is equal to sigma C, sigma R, sigma S. Of course, since sigma C is an involution, we just get sigma R, sigma S. We have a product of reflections in parallel lines. That must be a translation. Okay. So, well, what's the problem here? So sigma C gamma cannot be in F, right? Because all the translations in F are some power of tau, some integer power of tau, right? You're only allowed to apply tau or tau inverse to get all your translations. But here I have a translation of half the length of tau, right? I can't have that if all the translations are supposed to be generated by tau. Okay, so therefore, this translation, sigma C gamma, is not in F. Or rather, I'm sorry, what we really should say is that this is not in the subgroup of translations of F generated by just tau, which in turn implies that sigma C is not in F. Okay. So, furthermore, if F contains sigma L with L perpendicular to C, then F contains the half term. The half term sigma L gamma. Okay. You can verify this in a similar fashion, right? Look at the that is to say, again, gamma is just this product, sigma C, sigma R, sigma S, gamma L times, I'm sorry, sigma L times sigma C is is the product of two reflections in perpendicular lines, which is a half turn, right? Their directed angle measure off each other is 90 degrees. So their product of reflections in those two lines must be a rotation of 180 degrees, i.e. a half turn. Okay, and then we get the translational component here. Remember the angle addition theorem, a translation followed by a rotation is a rotation by the same degrees. It just has a different center. So this is, again, a half turn. Okay. So we've seen that if F contains a half turn, it must contain the half turn centered at A, this point that we chose a couple days ago, right? Depending on the situation that we're in. Okay. Okay, so in this case, we've reduced to F is in fact F22, right? F22, which let me remind you, is gamma, the group generated by gamma and sigma A. Okay. So, in other words, we're done. Those, in fact, are all 7 of the possibilities for the symmetry group of a Friese pattern, or a so-called Friese group. Okay. So, let's write everything that we did over the past couple days all at once in a compact fashion, just so we have some perspective on what we've accomplished. Okay, here's our huge theorem. Okay, so let's let F be a Friese group with center C and translations, the group generated by tau. contains a half turn. Suppose sigma A is in F. And if F contains a reflection in a line line perpendicular to C, center. Suppose sigma A, little a, is an element of F with A perpendicular to C. And finally, let gamma be the glide reflection with axis C such that gamma squared is equal to tau. Then F is one of the 7 possibilities. Okay. Now, I'll just remind you of the 7 groups that we've discussed. We have F1, the group just generated by tau. We have F11, which is the group generated by tau and sigma C. Okay, I have F12, which is the group generated by tau and the reflection sigma A. Okay, and we also have F13, the group generated by a glide reflection gamma. Then, of course, our second row is F2, the group generated by tau and the half turn sigma A. F21, which is the group generated by tau, sigma A, the half turn, and reflection in C, the center. And finally, F22, the group generated by a glide reflection and the half turn sigma A. Okay. This is what we've proven over the course of the past 2 sessions. Okay. I want to show you this subgroup diagram, which you can figure out just by looking at, at these algebraic expressions, but I think it's kind of nice to lay it out in a more visually oriented fashion. Okay, so I'm going to erase this now, but this is just to recap everything we've done in the past several days. So have the following subgroup relations between Friese groups. A nice looking diagram, in my opinion. So here at the bottom, we have F1, which is a subgroup of F11. This arrow with a hook on it means that this is a subgroup of, okay, you'll see that notation sometimes, especially if you carry on in algebra. F11 is also a subgroup of F21. Okay, now let's go back down to F1. F1 is also a subgroup of F12, which in fact is also a subgroup of F21. Okay. Furthermore, F1 is a subgroup of F2. And F2 is also a subgroup of F21. Now, what else is F1 a subgroup of? Perhaps not surprisingly, it's also a subgroup of F13, which in turn is a subgroup of F22. Got one more arrow. F2 is also a subgroup of F22. Okay. So let me just point out, remember the definition of F1. That's just the group generated by tau. F1 necessarily has to be a subgroup of any Friese group, right? And you can see that's the case because there's a path to any other group in this diagram from F1 that ends at that desired group, right? And that is, of course, using the fact that if F1 is a subgroup of F11 and F11 is a subgroup of F21, that means that F1 is also a subgroup of F21. That is to say, the property of being a subgroup is transitive. Okay? So this is the kind of result. This sharp Finite classification result is the brass ring in a lot of contexts in mathematics, right? If you can describe a structure that is meaningful in some physical capacity or in terms of some model or some system that is of interest to you for whatever reason, if you can classify all the types of structure that fit that object that you're interested in, you've done the most complete job that mathematics can often do. Okay, so this is a really nice result. Okay, there's one kind of nagging thing here, though. What does this notation mean? Why do I choose these subscripts and superscripts? I mean, obviously the F is for freeze, but 1, 2, 3, why these sub and superscripts? Well, I actually don't have a great answer for that. It's notation that was designed by Fies Toth, a Hungarian mathematician. But I can't tell you why he made those choices, but I can tell you what they mean and how they can help you remember what the meaning of each of these groups are. Okay, so meaning of sub and superscripts. Okay, so on this side of the board, we'll put what the subscripts mean. And over here, we'll put what the superscripts mean. All right, what does the subscript 1 mean? The 1 means, if you see a subscript 1 on any of these, it means that the group does not contain half-terms. And the subscript 2 means just the opposite of that, that the group contains half-terms. Okay, how about the superscript? Well, the superscript 1 means that the center line C is a line of symmetry. Okay, and the subscript 2 means that the center line C is not a line of symmetry. And what does 3 mean? Well, that just means it's the special case and it's generated by a slide reflection only. Okay, so again, I know it might seem that I say this quite often. This notation is kind of silly, right? For subscripts, 1 is a negative statement. For superscripts, 2 is a negative statement. Why? Why did they make it that way? I have no idea. But unfortunately, for historical reasons, we're stuck with that now.
Just wondering, aren't superscripts 2 and 3 kind of related because a glide reflection is not naturally a line of symmetry?
Yeah, well, I mean, that's true, right? But I'm saying something much more specific with three, right? Um, that is to say, uh, I'm saying that there is a generator that fixes line C that is not a reflection. Okay. But you're right, they are related. Okay. So I just want to give you some time to digest this, and then I'll say I've blathered on about how this is like a really nice result, but what's not so nice is if I give you a freeze pattern, how do you effectively determine what its symmetry group is? Well, it turns out it's really not that hard. There's a simple flowchart that we can write down of a series of questions you can ask yourself about a given freeze pattern to determine what its group of symmetries is. Okay, so let's talk about that now. And I can tell you right now that the homework for chapter 10 is just, oh, I'm sorry. Okay, I was cutting out there. I don't know if this is like a time-based thing because it was around the same time yesterday where this started to happen. Unless we've been having that problem all day and nobody said anything. Usually when I leave the frame. Okay, okay. So even when I'm like off frame like this, am I cutting out now? No. Okay. It gets worse, but it's not cutting out. Okay. Okay. Yeah, I apologize. So what I was saying is the next thing we'll do right now is to give you some effective conditions, some easy, somewhat easy way to, given an arbitrary freeze pattern, determine what the group of symmetries is, the freeze group is. Okay. So what do we want to see? Here's a series of questions in plain English that you can ask yourself and a flowchart to help you determine what freeze group a given freeze pattern has. Okay, so let's start at the top. Has half turn. Okay, say yes to the right and no to the left. Then the next question we should ask is, does it contain reflection in the center? C. Okay, and I'll ask the same question here on the no branch. Okay, So if I have a half turn and a reflection in the center C, then I know I'm F2, 1. If I have a half turn and I do not have a reflection in the center C, then I have to ask, is there a reflection not in C? And if no, then I'm just F2. And if yes, I'm F2, 2. Okay. Now let's go more down the no path. So if we have no half turn and we do have a reflection in center C, then I'm just F1, 1. Just to make this stand out a little more, I'll circle these so you can identify determinants a little more easily. Okay. Okay, so once I say there's no half turn and there's no reflection in the center C, I must ask, is there reflection not in C? Two branches here as usual, yes and no. If yes, there is a reflection, then I just get F1, 2. And if I'm no half turn, no reflection in the center, and no reflection not in C, then I must ask if there is a glide reflection. If yes, then I just get F1, 3. And if no, I just get F1. Okay. So this is how you effectively check what freeze group a given pattern has, right? You just have to look for these types of symmetries and follow the flow chart. Okay, so why don't we take 5 minutes here, and if you have your textbook with you, look on page 83. Okay, there's at the top of the page, there's figure 10.10. And there's 7 patterns there that you're supposed to identify the freeze group of each of those patterns. So why don't we take 5 minutes, and then in the last 5 minutes, we'll come back together, take 5 minutes, try to identify the freeze groups of each of those patterns. And then in the last 5 minutes, we'll come back together and discuss your answers. Okay? So do that.
I'm sorry, what page did you say?
It was page 83.
Oh, word.
Mm-hmm.
All right. So let's try to do a few of these together. In this first line in figure 10.10, we have the phrases separated by dots: me cook, he cook, we cook, and then we start he, see. What do we think here? Who can tell me what they believe the freeze group of this freeze pattern is?
Which was this again? What letter?
So it's this top line of figure 10.10.
Oh, okay.
So, well, let's ask ourselves, let's traverse this flow chart. First of all, does this first line, me cook, he cook, we cook, does this have a half turn? Yes or no?
No.
Yeah, okay, good. We got a couple no's, and that's right, because if you take any point through the center of the letters, take any point on that line and rotate by 180 degrees in either direction, you're going to get something not symmetric, right? For one thing, the K's will be backwards, right? Among many other things, the C's will be backwards, a bunch of reasons. So no half turn. Okay, so now, how about, do we have a reflection in the center line C? We take the line through the center of all those letters and reflect about that. Is that a symmetry of this line? Yeah, no, right. But almost, right? Because if we instead of we cook, it was another M, me cook, well, that still wouldn't work. But it's tempting to say that it almost looks like it, but it doesn't quite work. So no, there is no reflection in the center line C. Is there a reflection about a line which is not the center? Which, remember, during our investigation, we deduced had to be some line perpendicular to the center line C. So Keenan says he doesn't think so. Anybody else have any feelings on that one? Yeah. Jordan also thinks no, and that's correct. Again, if you just think about it, look at it, and any reflection will, again, say reverse the C or the E, right? You'll have things flipped. Certain letters will be flipped backwards of where they should be if it were a symmetry. Okay, so no reflection, not in C. We're down to the last question. Is there a glide reflection that fixes this pattern? Okay, so Keenan says no. Anybody else have any feelings about that? Well, so there is, in fact, a glide reflection. Okay. So what you'll want to do to construct this glide reflection, yes, exactly. Keenan said it on the nose. So with the glide, remember, a glide is a translation followed by a reflection. Okay. And if a freeze has a glide reflection, the axis of the glide reflection is the center line C. Okay. So in this example, me cook, he cook, we cook, all we do is translate the text. So the M is where the W was, and then flip about C, the center line, right? Because all the letters used in this text are symmetric about the line C, except for M and W, but they are mirror images of one another. So if you put the M where the W was and then flip, you'll get exactly what you had to start with. So therefore, we conclude, yes, there is a glide reflection. So our freeze group for that first pattern is F13. Okay, so I just want to write down a couple homework problems, and these homework problems are not very intensive. They're mainly just practice recognizing which patterns have which freeze groups. Okay, so let's just say homework. Finish figure 10.10. That is to say, why don't you go ahead and identify the freeze groups for all the other lines of text in that figure. And then let's do 10.4, 10.5, and 10.9 from the exercises at the end of the chapter. Okay, so that'll be it for today. Tomorrow, we'll start the very basics of how to classify the wallpaper groups. We'll define what a wallpaper group is and prove some basic properties about it. And let me tell you, it's very similar in spirit to what we've done here with freeze groups. Okay, the primary difference, just as a preview, is that the group of translations has exactly 2 generators. So instead of having a line of symmetry, there's some kind of 2-dimensional notion of what is preserved under my group of symmetries. Okay, so thanks everybody, and I'll see you all tomorrow, and I'll message you over Canvas shortly with the solutions to the practice exams. Okay.